One of the most active fields in AI at the moment is post-training. I have been covering a lot of tools over the course of last 2 years where you can use these tools to post-train a large language model on your own data set to align them according to a specific requirement. So what happens is that you take a new neural network, you train it on a world data, after that you have a base model. If you want to train or fine tune that base model on specific use case or specific task, you need to post train it. There are a lot of tools in the market already which we have covered on the channel, and Google has now just dropped this Tunix tool that focuses on the same post training stage but TPU specific. Also, it supports JAX, which is a native toolkit from Google. JAX is the compute engine underneath, which is a NumPy like Python library with automatic differentiation and just in time compilation that runs the same code on CPU, GPU, or TPU. TPUs are Google's AI accelerators. You can rent them in Google Colab, Cloud, or at some other places like Kaggle. They are designed to scale training, fine tuning, and work great with JAX. In very simple words, JAX is the engine, TPU is one of the tracks it runs on, and Tunix is the set of sort of crew tools for post training on that engine. In this video, I am going to explain this Tunix in very simple words. Also, we already have seen what JAX is, and I will also show you how you can post train your own model on your own data by using this Tunix library. I'm not going to do the full hands-on, but I will definitely share a notebook with you. So straight up, we will be checking out what are the steps in order to do so. This is Fahad Mirza and I welcome you to the channel. Please like the video, subscribe, and also consider becoming a member as that helps a lot. So what makes this Tunix different? Rather than being a heavy end-to-end framework, Tunix stays close to raw JAX and gives you small composable building blocks which comprise of losses, sharding, and trainer loops. It is aimed at post-training specifically on TPU, but you can use it on GPUs too. This design lets you carry the same recipe from a single TPU to multi-device setups or over to even TPU pods without rewriting your code. It also uses JAX transformation and accelerator portability. In addition to that, there's new technique which is Tunix. It ships ready recipes for supervised fine tuning where you can fine tune either full weights or you can simply use LoRa where you freeze the model and train tiny low rank adapter matrices inserted into the layer. You can even use it with QLoRa, which is same idea as LoRa, but the base weights are 4-bit quantized, so you can fine tune huge models on a single big GPU or TPU. And of course, you can use it with direct preference optimization. You can use it with reinforcement learning, with PPO, GRPO, and few other things which you can check out. By the way, if you prefer the PyTorch world, Hugging Face TRL covers SFT, DPO, PPO, and also plugs into transformer ecosystem, and that you can say is a equivalent of this Tunix if you want to draw the parallels. Also, Microsoft's DeepSpeed is another parallel which is equivalent to what Tunix is. Now, let me take you straight to the notebook where you can check out how to get it installed and use it. Now, if you look at this code, this gives you the whole overview as how you can get it installed. This is Google Colab. If you want to try it out, you would need to Google Colab, from there runtime, and then change runtime type, go to any TPU. I don't think so this is going to work with this TPU, with this model, but you can try out a lower model. But for bigger post trainings, you would have to buy some credits with Google Colab. And that is why I'm just going to show you how it works. So you see, first up, we are setting up the environment, we are installing all the dependencies and including Tunix and Quix from GitHub, and also the flags NNX, which replaces the pip flags so that the model uses the newer NNX API. And then we are defining the WAN DB. This is for observability. This is optional, but it gives you the full overview how the training is progressing. Then we are importing all of these libraries which we have installed. Then we are defining hyperparameters like batch size, if we are using LoRa, because this example is primarily using LoRa or low rank adaptation to fine tune a JAMA model. And then we are also logging in to track matrices. We are also using this command to create the directories. We are loading the model from Kaggle Hub, which is the JAMA model. As you can see here, you can also go with Quen if you like. And then we are getting the or downloading the base model. After that, we are also building a JAX device mesh and an NNX transformer after running this command. This is primarily around the JAX requirement, because Kaggle's checkpoint is not in NNX ready format. It is first loaded, resaved locally, and then reloaded as a sharded state mapped to the mesh. And that is why we are using all of these commands. Finally, you can see that here the sharded base model is reconstructed and displayed. So now we have a JAMA model in NNX form ready for Tunix post-training. Then we are initializing its tokenizer. We are giving it a prompt in different like French, whatever language you want to use, you can use that. This is where we are applying the LoRa or low rank adaptation, as I mentioned earlier. Now, just to give you a very quick background, what LoRa is that instead of updating billions and billions of original weights, LoRa learns a small low rank update, which are just very small two skinny matrices A and B that approximate how those big weights should change. And we just train these small adapters and combine them with the frozen backbone at inference time. That dramatically cuts trainable parameters and memory without a big quality hit. So what this code is doing, as you can see, it is wrapping our base JAMA model with LoRa QLoRa adapters on specific projection layers, Q value or MLP, and it uses a Quix LoRa provider. Standard LoRa adds tiny low rank matrices, and then it trains only those while keeping the original weights frozen. And after that, we are simply loading the data set and we are training our model. It's a simple thing which we have done a lot of time on the channel. This is where we are combining the data set with the model, and then we are training it out. And then it is going to do the inference with the updated modes. So if you want to learn more about how this inference works, training works, I have done heaps of videos where I have actually shown you how to do it hands-on. And you can just go to channel and search with fine tune. These are all the videos, heaps of them, where we have done it in a hands-on way. But this video was more about just an introduction to Tunix, just to give you another option. So specifically, if you use TPU, then instead of going with other options, I would suggest going with this Tunix, because if you are post-training a huge model with a huge data set, this is definitely going to give you a lot of speed grunt. That's it. Let me know what do you think. If you're already using TPUs, please let me know in the comments, because I really can't understand why Google doesn't sell TPUs to the consumers. There's a huge market for it. Thank you for all the support.